Everybody, welcome back. Today we're going to finish up section 2.3. So this is where we are going to start right here. Sketch the graph, describe the domain, and then describe the continuity of each function. So let's start. Hopefully you can find that in your notes. This should be right where we left off from the last video. Okay, let's sketch a graph of 1 over x. So that looks like this. And we have an asymptote at x equals 0. Okay, so that's the graph. And the domain is negative infinity to 0. And that U stands for union. And then 0 to infinity. And if you see I have brackets, that means 0 is not included. And a shorter way of saying that is x cannot equal 0. So we have a discontinuity at x equals 0. Okay, all right. This function right here, what we can do is we can factor the top. So that's the difference of two squares. So that becomes x plus 1, x minus 1. That's an important pattern to know. Divided by x minus 1. So those cancel. And remember from our notes prior, this is called a removable discontinuity. So the graph is actually just going to look like x plus 1. So the graph of x plus 1 is going to have a y-intercept of 1. It's going to go up 1 over 1, so like that. But x cannot equal 1. So we have an open circle here at 1. So our graph would look like that. So there is, in this case, a discontinuity at x equals 1. Okay, so the function is continuous except at x equals 1. And in this case, this function is continuous except at x equals 0. Okay, let's take a look at these two examples. H of x is equal to x plus 1 when x is less than or equal to 0. So let's go ahead and draw that part out. So when x equals 0, h of x is equal to 1. So we have a point at 0, 1. And that's going to be a closed circle because it's equal to. And then that's just a line with a slope of 1. And then for all values greater than 0, so it's going to get infinitely close to 0, but not at 0, we have x squared plus 1, which is a parabola with a vertex at 0, 1. So it looks like this. So this actually is a continuous function. So I would never have to lift my pencil up, and the limit from the left is equal to the limit from the right at all values on that function. Okay, and then finally y equals sine x. Looks like this. Remember, draw that. And this is, oh, I should have written the domain here. So the domain is all real numbers, and this is a continuous function for all values. And the domain here is also all real numbers, and it's continuous. Okay? So this is describing the domain and the continuity of these four graphs right here. So let's formalize this. A function is continuous on an interval if and only if it is continuous at every point of that interval. It's an R, whoops. So going back to our example back here, if our interval was from -1 to 1, this function is not continuous on that interval because we have a discontinuity at 0. Same thing here. If our interval was from 0 to 10, that would not be continuous on that interval because we have a discontinuity at 1. Okay? So for a function to be continuous on an interval, it has to be continuous everywhere on that interval. Now, a continuous function is different. A continuous function is one that is continuous at every point of its domain. Okay, so let's take a look at these two examples, and we'll talk about these two. F of x is equal to square root of x. That's like this. So let's think about this. The domain of square root of x is 0, which is included, to infinity. So from 0 to positive infinity, is this function continuous? And yes, it is. So therefore, this is a continuous function. Because it's continuous on its domain. Okay, this function right here, I don't know if you can recognize it, but actually is a semicircle. From -1 to 1. You could put that in your calculator if you want. And it looks like this. That's a little crooked, but you get the idea. And actually, this value is included. So if I put in a -1 here, I get the square root of 0, which is 0. So square root of 0 is defined. So the domain for this function, actually I usually do a colon there. Okay, so our domain is -1 to 1. And is our function continuous on that interval? Yes, it is. So this is a continuous function. Because it's continuous on its domain. I think in your notes you have one more. F of x is equal to 1 over x. And that looks like this. And the domain are all real numbers except for 0. And it actually is continuous on those. So the domain is x cannot equal 0. And it is continuous on its domain. So this is a continuous function as well. Okay, so what types of functions are continuous on their domain? Well, quite a few. So polynomials are one. Rational functions. Even though rational functions usually have a discontinuity because they have a variable in the denominator, on their domain they're continuous. Absolute value functions are continuous. And exponential functions. Logarithmic. Our trig functions are continuous. And radical functions. That just seems like about everything, doesn't it? I forgot a C in there. Okay, so those are functions that are continuous on their domain. Now here's a note. If f is continuous and g is continuous, then the composite function f of g of x is continuous. So let's apply that. So if we didn't have access, we couldn't use our calculator and we were wondering if this was continuous, we could break this into parts. So let's think about sine of x, just the outside function. Sine of x is continuous, we know that. Just that periodic function, the domain is all real numbers. And x squared plus 1 is also continuous. And because we know these two components, sine of x squared plus 1 is also continuous. And we know that because each of the parts are continuous. We wouldn't even need to use our calculator. We could just know that from each of the parts. Okay, and then the last topic we're going to talk about seems really logical, and it is. It's called the intermediate value theorem. Sometimes I'll write that abbreviation, but we won't write that on any types of assessment. We'll actually spell it out. We don't use abbreviations for our AP assessments, but IVT, intermediate value theorem. And what this theorem says is that if a function is continuous on an interval, and the starting point is not the same as the ending point, k is any number between those values, then there is at least one number in between those two values. So that's a real confusing definition. But let me explain it to you, and we've even talked about this before. So first of all, a person's height is a continuous function. You don't just wake up and in one instant you grow 2 inches. You grow continuously. So let's say that you start with a height of 52 inches in the year 2016. That's your physical. And then by 2019, you are 58 inches tall. You know that between 2016 and 2018, you were all those heights in between 52 and 58. So for example, were you ever 54 inches during those 3 years? Yes, you were. You may not know when you were 50. I forgot what I said. Did I say 54? Okay, let's say I said 54. You don't know when you were 54 inches tall, but at some point you were 54 inches tall. So this is called an existence theorem. We don't know where, we just know that it existed at some point. So this is the intermediate value theorem. So at some point between 2016 and 2019, you were 54 inches tall. Okay? So let's use this in a more abstract way. We're going to use the intermediate value theorem to show that the function has a 0 on the interval 0 to 1. And a 0 means the function equals 0. So let's first evaluate f of 0. And f of 0 is 0 cubed plus 2 times 0, that's 0. So that equals -1. And f of 1 is going to equal 1 cubed plus 2 times 1 minus 1, which is equal to 2. So I know that between 0 and 1, the function at some point equals 0. So let's sketch that out. So if I start at -1, and then at f of 1, I'm up here at 2, I don't know what the behavior of the function is in between, but I know somewhere between 0 and 1, my function is equal to 0. So because f of x is continuous, and when you're using the intermediate value theorem, you have to establish that it's continuous. There is some value, I'm just going to call it c, where f of c is equal to 0. So we don't know where between 0 and 1 that is. We just know that somewhere f of c is equal to 0, that we have a 0 on that interval. Okay, so that's the intermediate value theorem. This wraps it up for section 2.3. Thank you.